Hello everyone, welcome back to my channel. Now I'm going to head over to one of the most complex and confounding topics of what we call it as time complexity. Bear with me because it will have a little bit of mathematics involved in order to analyze stuff and some kind of logical thinking. The analysis of time complexity is what we also call it as asymptotic analysis. Moving further, what is time complexity? So is time complexity depend on the length of the code, or does it depend on the machine or the programming language we're writing the code in? Or is it the time that is required to execute the code? To answer these questions, I'm going to show a small demonstration onto the most popular and common coding languages, that is Python and Java. Heading over to the demonstration, first I'm gonna introduce you to a small Java code. The length of the code is just 5 lines, and I'm just importing a library which is called time. I'm taking the start time, printing a statement called hello guys to the console, and taking the end time, finding the difference between end and the start time, multiplying it with 1000. Since the answer is rendered or returned in the form of seconds, I want it in milliseconds. So executing the following code, I will print hello guys and as well as the time it has taken to execute the following code. First, I've executed once. It shows it almost takes 0 time to execute the code since there is only one statement out there. I execute it again. It gives me certain values to certain times. It gives me a particular value. So I assume it almost took 1 millisecond in order to execute the code. I'm gonna execute the same code which is syntactically different in another programming language. You can check out the lines of the code. That is 4, 5, 6, 7, 8, 9, 10, 11, 12, including the curly braces. So officially, according to the question, if time complexity is dependent on the length of the code, or if it depends on the programming language of the code, then this code should take more time if it depends on the length of the code. You can have a look at the answer. I've just imported a file, or a library called math in order to multiply it and convert. It returns this system.nanotime returns the value in nanoseconds. So to convert that into milliseconds, I've used a function from a library called math.pow that it calculates the power of 10 raised to 6. Power of 10 to 6 minus 6. Executing the following code, what I get is, hello guys. Okay, I'll just clear out the screen so that it does not show me the previous output. So hello guys, it took nearly 0.07 milliseconds. So coming back to the evaluation, what is time complexity? So first of all, to the first question, does it depend on the length of the code? No. I've already illustrated it. It does not depend on the length of the code. Second, does it depend on the programming language? So Python, which took more time to execute the code since it's an interpreter language, and Java, it is an interpreter and a compiler language. So hence, it executes the code way more faster and efficiently as in comparison to Python. So does it depend on the programming language? Yes, the execution time of the code depends, but the time complexity does not depend on the programming language. And finally, is it the time required to execute the code? To answer this question, I would say yes, partly yes. It does depend. It is the time required to execute the code, but it is the time that is required to execute. The perfect answer to the question is it is the time that is required to execute a particular statement in the code. So how do we define time complexity? Time complexity is nothing but a mathematical evaluation of a program when it is given different number of inputs. So it is depend on the number of inputs and how much time does a statement in a code take to execute in a particular program. We looking back into our previous codes. One was in Python that was executing the same code that is printing the output to the console, and Java was also executing the same code, which is printing the output to the console. So to execute a particular statement, both of them were taking the same amount of time. So both of their time complexity is constant. So when we write a code, comparing both of these codes, they have the same time complexity. So it is the time that is taken to execute a particular statement in the code when given a sufficiently large amount of inputs. So what is time complexity? It is nothing but a function of n, where n is the number of inputs given to a particular program. So categorizing time complexity, it is a mathematical representation of the performance of a particular program, which is categorized into the best case, worst case, and the average case. What is the best case? Best case is the best possible performance of a particular program. Worst case is when it is provided with the most largest set of inputs or the most complex set of inputs to a particular program. What is its performance? And average case is what I'm going to discuss further in the further part of the video. So when we call, these are some of the notations that we use in order to define time complexity. First and foremost is what we call it as the big O notation. The big O notation is also called as the asymptotic upper bound or the worst case. That is, when we provide a sufficiently large amount of input that is pretty complex for a particular program, we test the performance of the program in that case. Is what we call it as big O notation. So when we say f of n is O of g of n, which means the function f of n does not grow faster than g of n. What is g of n? G of n is the function or the performance matrix that we have considered for a particular program, and we are evaluating that, where n is also the number of inputs. That is the graph of g of n and f of n, where f of n is lagging behind. It does not go faster than g of n, where g of n is the function that we are measuring. What is omega notation? Omega notation is what we call it as the asymptotic lower bound or the best case. The best case analysis of a particular program when it is given with the minimum set of operations or minimum complexity. What is the performance of a particular program is indicated by omega notation. Here, the function f of n does not grow slower than g of n. So it's either equal or faster. Similarly, f of n is the function of time complexity, n is the number of inputs, and g of n is the function that we have considered for a particular program, or we have calculated or estimated for a particular program. And then we have the final notation is what we call it as the theta notation. Coming over to the theta notation. Theta notation lies between the upper bound, that is the big O notation, and the omega notation. It grows equally with g of n, where n is the number of inputs, g is the function that we have considered, and f of n is the function of time complexity. You can have a look at the graph. For increasing value of n, f of n grows equally with g of n. Let me give you a small example about how do we calculate the best case or the worst case for a particular value. The best case of, say, we are searching an element in an array. So if the element is present at the first position of the array, then the time that is required in order to execute the array is a constant time. What do you mean by constant time? When it does not depend upon the input n. That is the best case. And what is the worst case? The element is not present in the array. So it will take you O(n) complexity, which means it will depend on the length of the array to find to check whether the input element is there or not, and finally it will come to an eventual conclusion saying that the element is not there in the array. Looking over to some of the most commonly or most simple asymptotic complexities is we have first O1 that defines the time complexity that gives us constant time. The program that we had executed here, it executes in constant time because it only has to print a particular statement to the console. So if in case we have a loop to print it, so we take the input n, let's assume n is equal to 10 for I, and I is equal to 0, I less than n, sorry, my bad, I less than n, I plus plus. So system.out.println hello guys. So here it takes a certain time n in order to, so it will print to the console n times. So now it has started depending on n. So it has O(n) complexity. So what if I have, say, system.out.print hello everyone. What is the time? This takes O of constant time, but this eventually takes n time because it depends on the input n, the loop. Whenever we have a loop, it depends on a constant time n. So what will be the time complexity of the program? It will be nothing but a summation of both of them. So complete time complexity will be, so what we say, the O of f of n, sorry, f of n will be, or you can say, you can also mention it as t of n. T of n will be nothing but O of 1 and plus O of n. Which one do you consider? You always consider the time complexity of the larger operation to be executed, which is n in this case. So hence, the time complexity of this program is going to be O(n). I'll just execute the code, and you will have a look that it will take a larger time in order to execute this particular code. You can just compare. Now it has taken round about 0.2 milliseconds in order to execute this code, and it has executed hello guys n times. N is 10 in this case. 3 plus 3 plus 3. One hello guys out here, so I was just a little finding out where it is. You have to print hello everyone and print Helen. So that's how it is. So we have 0.2 milliseconds here, and before, when we were just printing hello guys, we had 0.07 milliseconds. So that determines the time complexity of a particular program. What if I just have two loops in this, and I equals 0, well, in j equals 0, j less than n, j plus plus, and I have another loop, say for, I'll just copy this, and I'll just print hello everyone n times. So now this goes round about O(n) complexity, and this goes round about to O(n) square complexity, because this loop executes 10 times, but for each time this executes another 10 times. So the total number of time it executes should be round about 100. That is what we are expecting the output for. So for each I, it will print hello guys. So let's look into the output. It's gonna take a lot of time, I guess. So you can just have a look. It will be printing it 100 times, and now the amount of time it takes is 1.46 milliseconds. So that is now the time complexity of this particular program is n into 2, that is n squared, or I can just say this, it show it with the caret sign, that is n squared. So what is the overall time complexity of the program? We will take the higher time, that is O(n) squared. So this is the graph that signifies of what is going to be the time complexity of how we measure the time complexity of a particular program. The time complexities that we have is x cubed, that is if we have a three-dimensional array. If we have three-dimensional array, the time complexity is going to take to iterate through each part of the array is going to be OX cubed. And then we also have exponential time complexities, that is 2 raised to x, and then we also have factorial time complexities. So we are going to deal with such kind of complexities when you head over to competitive programming. Then coming over, what is the average case? We haven't discussed average case yet, and neither there's another prominent term that is being used. We'll be discussing that later. So first of all, coming over to average case, it is nothing but the sum of all cases divided by the total number of cases. So what is sum of all cases? Sum of all cases is defined by all the possible cases. So let us say if we are searching an element of the array, we have discussed the best case, that is the element is present at the first position. What is this worst case? The element is not present at all. So what if the element is present at any part of at any other position in a particular array? So how do you explain that? So for that, we evaluate the average case of that particular array. So how do we calculate the average case? So for that average case, in order to find the element that is present at the minimum position, so it can be at the first position, it can be at the second position. So it takes 2 positions, that is, in order to move to 2 positions in order to search for that element, it can take 3, or it can be at the nth position of the array. So this is the total number of cases, or total number of possible cases divided by n. So by the sum value, we get it as n into n plus 1 divided by n, which is nothing but which equates to O(n) complexity. We will head over in detail about average complexity further. I'll make a video of it if you want to have more clarity about average case. So that is the general idea of how we calculate an average case of a particular problem. And further, what we have is what we call it as amortized analysis. So in case of amortized analysis, the formula is get the worst case and divide it by the total number of cases. So the amortized value is O of n raised to 2 divided by n. So that will be roundabout will give you O of n. That is the amortized value of this program. The most common example of amortized analysis is evaluating or calculating the time complexity or the amortized time complexity of a dynamic array, which I'll be explaining in the next video. Thank you for watching. Please like, share, and subscribe my channel if you want to have more broad content. Thank you and have a nice day.